Welcome back, students. Today we are going to deal with the topic Law of Conservation of Momentum and its application from the chapter Force and Laws of Motion. So, this law deals with momentum, something related to momentum, and the law states that for an isolated system, the total momentum always remains a constant. That is, if no external forces acts on a body, always the total momentum of that body will remain the same. The law will become more clear when we do the derivation part. Okay. So, now let us see the derivation part of this law. So, the law is the total momentum of a object or a system always remains the same until it is acted upon by an external force. If the system is isolated, if there is no force acting on that system, the total momentum of that system always remains the same. That is the law. The total momentum of an isolated system remains unchanged. This is the law of conservation of momentum. To make the law more clear, let us come to the derivation part. For that, let us consider two objects, object A and object B. Let mass of object A be ma and mass of object B be mb, and this ma was moving with an initial velocity ua and the second object is moving with an initial velocity ub. Okay, so we have two objects, object A and object B. The mass of object A is ma and the mass of object B is mb. Both the objects are in motion, so they have an initial velocity ua and ub respectively. Now, let us consider this ua is greater than ub, which means the first object is travelling with a greater speed than that of second object. ua, the velocity of the first object, is greater than the velocity of the second object, means first object is moving faster than the second object. So, there is a chance of collision. So, after some time, both the objects, both object A and B will collide, and after collision, object A will be moving with another velocity Va and object B will be moving with another velocity Vb. So, during collision, forces will be acted upon between these two objects. That is, during collision, the object A will exert a force on B. Let us name it as FAB. During collision, this object A will exert a force on object B, which is represented as FAB, and in turn, according to Newton's third law, object B also will exert a force on first object. Let it be FBA. So, since both the velocities are different, there is a chance of collision between the two objects, and during collision, the first object will exert a force on the second object, and in turn, the second object also exert a force on the first object. And let us name those forces as FAB and FBA. That is according to Newton's third law. Now, since they experienced a force while they collide, definitely their velocities will change. We know that when a force acts on an object, their velocity or their speed will change. So, after collision, the objects will move with different speeds. So, initially they were having a speed of UA and UB, but after collision, their speeds will change to VA and VB. Even after collision, due to the force experienced by them, they will move but with different velocities, that is VA and VB. So, this is the case. Okay. So, this is the case before collision. This is the time of collision. This is the case of the objects after collision. Okay. Now, let us see. So, we are interested in momentum. We are going to state or derive law of conservation of momentum. Now, let us see what is the momentum of this system before collision. So, now let us see the case of before collision. So, before collision, let us see what is the momentum of ball A. We know that the formula to find momentum is mass into velocity. So, here for ball A, mass is ma and velocity before collision is ua. So, momentum of ball A before collision is mass of ball A into velocity with which it was moving, that is ma into ua. Similarly, momentum of ball B before collision. Again, the mass of ball B is mb and before collision it was moving with a speed ub. So, formula is mass into velocity, that is mb into ub. So, these are the momentum of both the balls before collision. Okay. Now, similarly, let us see the case of after collision. We know that during collision, both the objects experienced force. As a result, their velocity changed. So, definitely their momentum also will change. Since they experienced a mutual force on each other during collision, their velocity got changed after collision. Since the velocity has changed, according to the formula, momentum is equal to mass into velocity. If velocity changes, its momentum also changes. So, now let us see what are the momentum of the two balls after collision. So, after collision, the first ball is moving with the velocity VA. So, momentum of ball A is mass remains the same, that is MA itself, into velocity after collision is VA. Similarly, momentum of ball B is, again, mass of ball B is the same, that is MB, into velocity of ball B after collision is VB. So, mass into velocity here is VB. So, these are the momentum of ball A and ball B after collision. MA, VA and MB, VB are the momentum of both the balls after collision. Now, consider the case of ball A. Consider the case of ball A. Okay. So, before collision, momentum of ball A was MAUA, and after collision, momentum of ball A is MAVA. So, initial momentum, that is before collision, is MAUA, and after collision, the final momentum of ball A was MAVA. Now, let us see what is the change of momentum for ball A. To find change we need to subtract change of momentum. So, to find this change, we need to subtract the momentums, that is final momentum minus, since it is a change, we need to subtract. So, PF minus PI. Since we are finding a change in momentum, we need to subtract the initial momentum from the final momentum. Now, according to, now let us see what is rate of change of momentum. Rate of change of momentum. So, change of momentum is final momentum minus initial momentum. The word rate of, as we have discussed in Newton's second law, the word rate of means divided by time. The word rate of means divided by time. So, rate of change of momentum is PF minus PI by T. Now, let us substitute the values of PF and PI. So, rate of change of momentum is PF. What is PF? It is MAVA. So, PF is MAVA minus PI. PI is MAUA. So, instead of PI, substitute its value MAUA divided by time. Now, according to Newton's second law, we know that rate of change of momentum, is proportional to the force. So, for here the force is, during collision, the ball, we are dealing with ball A now. So, during collision, the ball exerts a force on ball B and the force is FAB. So, here, according to Newton's second law, rate of change of momentum is proportional to F. Now, in case of ball A, rate of change of momentum is MAVA minus MAUA by T. This is the rate of change of momentum for ball A is proportional to the ball A exerts a force on ball B and the force is named as FAB. So, rate of change of momentum is proportional to force. Now, to change the proportionality sign, let us multiply with a constant, that is MAVA minus MAUA by T is equal to, let the constant be 1 into FAB. To change the proportionality sign to equality, we multiplied with a constant and let that constant be 1. So, the equation became MAVA minus MAUA by T is equal to FAB. Let this be equation number 1. This is the case of ball A. Now similarly, can you write for ball B? Similarly for ball B, can you formulate a similar equation for ball B? Now for ball B also, rate of change of momentum is equal to the force exerted by ball B on ball A. So to find rate of change of momentum for ball B, instead of MA, since we are dealing with ball B, it is mass of ball B into velocity of ball B minus initial momentum of ball B, that is MB into UB, divided by rate of, means divided by time. By comparing this, we can write an equation for ball B, which is equal to the force exerted by ball B on ball A was FBA. Mark this as second equation. Now here we can see that in the picture, we can see that when ball A exerts a force on ball B in the forward direction, according to Newton's third law, the ball B exerts a same equal force on ball A but in opposite direction. This FAB and FBA are equal but opposite in direction. So according to Newton's third law, according to Newton's third law, the forces are equal and opposite. That is FAB and FBA are equal but in opposite direction. So to show the opposite direction, we put a negative sign in one of the forces. Both the forces are equal but they are opposite. So to show that opposite direction, we put a negative sign. Okay. So now let us see equation number 1 and 2, how it changes. So equation 1 is MAVA minus MAUA by T is equal to FAB, and equation 2 is MBVB minus MBUB by T is equal to FBA. Now according to Newton's third law, both the forces are equal but in opposite direction. So FAB and FBA are equal but they are opposite. So instead of FAB, let us substitute its equation. So instead of FAB, so according to Newton's third law, FAB is equal to minus FBA. So instead of FAB, let us substitute its equation from equation number 1. FAB is equal to MAVA minus MAUA by T. So instead of FAB, I wrote its equation from equation number 1 is equal to minus FBA. So instead of FBA, I can go for its LHS part. because FBA is equal to MBVB minus MBUB by T. So, instead of FBA, let us substitute its equation, that is MBVB minus MBUB by T. I just substituted the equation for FAB and FBA from equation 1 and equation 2. Now, T and T got cancelled off. Remaining is MAVA minus MAUA is equal to minus of MBVB minus MBUB. Now, in the next step, let us open the bracket. Let us open this bracket. Minus of MBVB, that is minus MBVB. Now, minus into minus becomes plus. Minus into minus becomes plus, plus MBUB. Now, let us bring all U terms to one side and V terms to the other side. All the terms that include U to the left hand side and all the terms that includes V to the right hand side. We are just going to rearrange the equation. Okay. Now, here already I have a term with U, that is minus MAUA. Now, from this side bring MBUB to the other side. So, it becomes, here it is plus. So, when it moves to the other side of the equation, it becomes minus MBUB, which is equal to, already I have minus MBVB in the right hand side. Now, bring this MAVA to the right hand side. So, here it was positive MAVA. When it moved to the right hand side, it becomes minus MAVA. Now, in this equation, in this side, minus is common, so I took it outside. So, it becomes minus of MAUA. I took minus outside, so here it becomes plus MBUB equal to, again here also let me take minus as a common sign, it is outside. So, it becomes MBVB. I took minus outside, so it becomes plus MAVA. So, in both the sides I have minus, so they got cancelled off. So, the equation becomes MAUA plus MBUB, which is equal to MAVA plus MBVB. That is, this is the momentum of ball A before collision. This is the momentum of ball B before collision. So, the sum of momentum of ball A and ball B, this is the sum of momentums of ball A and ball B before collision. Collision മുൻപ് ball A യുടെയും ball B യുടെയും total momentum ആണ് ഈ left hand side ൽ കാണുന്നത്. This is the total momentum of ball A and ball B before collision. Now, here coming to right hand side part, MAVA is the momentum of ball A after collision, and this MBVB is the momentum of ball B after collision. So, here right hand side depicts the sum of momentums of ball A and ball B after collision. Ball A യുടെയും ball B യുടെയും total momentum after collision. That is the RHS part. So this is the total momentum of ball A and ball B before collision, and RHS depicts the total momentum of ball A and ball B after collision. And we proved that before collision and after collision the total momentums are equal if no external force acts on it. That is, total momentum before collision will be equal to total momentum after collision. This is the mathematical formula for law of conservation of momentum. That is MAUA, total means plus, MBUB. UA and UB are the velocities before collision. So total momentum of both the objects before collision is equal to total momentum after collision. So after collision, momentum is MAVA and MBVB. Total momentum, so we need to plus it. Both are equal. This is the mathematical formula for law of conservation of momentum. If no external force acts on a system, the momentum remains unchanged. Before collision and after collision, the momentum remains the same. It will be equal if no external force acts on it, or if the system is isolated, its momentum will remains the same. So this is the mathematical formula of law of conservation of momentum. That is, total momentum before collision is equal to total momentum after collision. That is, MAUA plus MBUB is equal to MAVA plus MBVB. Hope the derivation is clear. So we had two objects of masses MA and MB. Initially it was moving with velocities UA and UB. Since one of the velocity is greater, they will undergo a collision, and during collision they experiences a force. Ball B experiences a force due to ball A, that is FAB. In turn, ball A also experiences a force due to ball B, which is equal to BA. Both the forces are equal but opposite in direction. So since they experience a force during collision, definitely they will have a velocity change after it. So after collision, both the balls will be moving with different velocities VA and VB. So these are the three cases: before collision, during collision and after collision. Now we found out the momentum of ball A and ball B before collision. The formula to find momentum is mass into velocity. Using that formula, we found the momentum of ball A and ball B before collision. We also found the momentum of both the balls after collision with the changed velocities. Again, the formula to find momentum is mass into velocity itself. So we found both the momentums after collision. Now the next step was, we found the change of momentum. To find change of momentum, formula is PF minus PI, where PF is the final momentum and PI is the initial momentum. Now next step is rate of change of momentum. Rate of means divided by time. So it becomes PF minus PI by T. Now we just substituted the values of PF and PI in the equation. So the equation became rate of change of momentum is MAVA minus MAUA by T. Now, we are going to apply Newton's second law into that. According to Newton's second law, rate of change of momentum is proportional to force. We just substituted the equation for rate of change of momentum and the force, and we got the first equation for ball A. Similarly, we wrote a similar equation for ball B. So, we got two equations, one for ball A and one for ball B. Now, we know that according to Newton's third law, both the forces are equal but opposite in direction. So, we just substituted FAB and FBA in the equation of Newton's third law. Remaining all the steps are just simplification, just rearrangements. We just took all the terms having u to one side and all the terms that are having v to the other side, and finally derived the equation for law of conservation of momentum. The derivations seem to be bigger, but it is easier if you write and learn. Okay, so understand, write and learn. Don't just don't mug it up. Understand each and every step, then write and learn. So the derivation will become more easier. If you try to mug it up, it becomes confused. So understand and learn. Okay, so this is the law of conservation of momentum. Hope the law and the derivation part is clear. Now let us move on to its applications. First application is of the gun and the bullet. The gun and the bullet. This is the case of before collision. Before collision, both the gun and the bullet was at rest. So, before collision, both gun and bullet was at rest. So, initial velocity of gun is equal to 0. Initial velocity of bullet is also 0. Since both are at rest, their initial velocities are 0. Now, according to the formula of conservation of momentum, the total momentum of this system before collision is MAUA plus MBUB. Here, instead of the first object, we have gun. So, MGUG, the equation becomes MGUG plus second object is the bullet. So, MBUB, mass of bullet into velocity of bullet before collision. Mg is the mass of gun and Ug is the velocity of gun before collision. And we know that before collision, both were at rest. That is Mg, Ug is 0 plus mass of bullet into velocity of bullet before collision. It is also equal to 0 since the bullet and the gun are at rest. Now Mg into 0, that is 0 plus Mb into 0, which is equal to 0. So before collision, the total momentum is 0. Before collision, the total momentum is 0. Now let us see the total momentum after collision. So first case is recoiling of gun. In this case, we have two objects, a gun and a bullet. Let mass of gun be mg and mass of bullet be mb. So initially both gun and the bullet was at rest, so their initial velocity will be 0. Now after collision, that is after the bullet is being fired, Their masses remains the same, but the gun will recoil. So it attains a velocity when bullet moves forward. When it is being fired, the bullet will attain a velocity Vb in forward direction, and according to Newton's third law, when bullet moves forward, the gun will recoil in the backward direction. So the gun will attain a velocity Vg in the backward direction. Okay. Now, according to law of conservation of momentum, total momentum before collision, that is MAUA plus MBUB. This is the total momentum before collision. So instead of the first object, here we have gun. So MGUG plus, instead of the second object, here we are having our second object is the bullet. So mass of bullet into velocity of bullet. We know that mass of gun, initial velocity of gun was 0 since it was at rest, plus mass of bullet into initial velocity of bullet is also equal to 0 because both gun and bullet were at rest. Mg into 0, it is 0. Mb into 0 is also 0. So total momentum before collision is 0. So total moment, this is the case of before collision. So total momentum before collision is 0. Now let us see the total momentum after collision. Okay, let us see the total momentum after collision. So according to law of conservation of momentum, MAUA plus MBUB is equal to MAVA plus MBVB. Here, instead of the first object, we are having gun. So we are just rearranging the equation into our terms. So instead of first object, we have gun. So MGUG plus second object is bullet. So MBUB is equal to, again, first object is gun. So MGVG plus second object is bullet. So MBVB. Already we have found that before firing, the total momentum before firing is 0. Already we found that. This is the total momentum before firing. We already found it as 0. So 0 is equal to MGVG plus MBVB. Now take this MBVB to the other side. So here already we have MGVG. Now we are going to take this MBVB to the other side. So it was plus here. So when it moved to the other side, it becomes minus MBVB. That is VB is equal to minus, take this MB to the other side, minus MB to the other side. So minus, when it moved to the other side, becomes divided by MB. When here it was MB into VB. So when MB moved to the other side, becomes divided by MB. So it becomes MG divided by minus MB into VG. Okay. So this is the equation for velocity of bullet. Now substitute this equation in our equation number 1. Let this be equation number 1. So substitute velocity of bullet in equation number 1 and we get MGUG plus MBUB is equal to, equation number 1 is MGVG plus MBVB. This is equation number 1. Substitute equation number 2 into equation number 1. We get, let us substitute it, MGUG plus MBUB. We have already found it as 0 equal to, നമ്മൾ already കണ്ടുപിടിച്ചു, before firing the total momentum is equal to 0. We have already found that. So LHS part is already 0. Now let us see the right hand side part. MGVG plus MB into VB. VB is mg by minus mb into vg. So instead of vb, let us substitute this equation, that is mg by minus mb into vg. See, mb and mb got cancelled off. So equation become mgvg plus into minus, it becomes minus sign, minus mgvg. mgvg minus mgvg, it is equal to 0. So we solve that left hand side and right hand side are equal. That is total momentum before firing and total momentum after firing are the equal. That is, the momentum is conserved in case of recoiling of gun before firing and after firing. So before firing the total momentum was 0. Here after firing its velocities will adjust. When velocity of bullet moves in forward direction, the gun will recoil in backward direction. By adjusting its velocities, its momentum remains the same. It will conserve its momentum by adjusting the velocities. Okay, so this is the first case of conservation of momentum. Now second case is man and the boat. Okay, so initially when the man was standing in the boat, initially the boat and the man was at rest. So both boat and the man was at rest. So initial velocities are 0. Since initial velocities are 0, their total momentum will be also 0. This is a case of before jumping. Before jumping from the boat, both boat and man was at rest. So their total momentum will be also equal to 0. Now let us see the case after jumping. When the man jumps, he is moving forward. He is having a velocity in forward direction. When he jumps in forward direction, according to Newton's third law, the boat will move in backward direction. So the boat will attain a velocity Vb in backward direction. This is according to Newton's third law. When man jumps forward, the boat will move backward. The boat will move backward. That is according to Newton's third law. So man will have a forward velocity and the boat has a backward velocity. So the velocity gets adjusted so that the linear momentum is, their total momentum after jumping also gets conserved. In such a way, their velocity gets adjusted such that the total momentum of the boat and the man after jumping remains a constant. Now the third example is motion of rockets. So initially the rocket was at rest. The gases inside the rocket was at rest. So their total momentum before the rocket moves is 0. Since their initial velocities are 0, the total momentum of that system is also 0 before the rocket moves. Now, when the rocket starts moving, the rocket is moving up with a velocity Vr. At the same time, according to Newton's third law, this burning gas will come out with a velocity Vg in the downward direction. So, their opposite velocities helps them to conserve linear momentum. Just in the case of recoiling of gun, their velocity will adjust themselves in opposite direction to conserve its linear momentum, and hence here the velocity of rocket is in upward direction and velocity of gases that is coming outside is in downward direction. This opposite velocity helps the system of rocket and the gas to conserve linear momentum. So, these are certain applications that relates the law of conservation of linear momentum. Hope the topic is clear. So, the law is, if no external force acts on an object, its total momentum will remain the same. And the equations are MAUA plus MBUB is equal to MAVA plus MBVB. This is a mathematical formula of law of conservation of momentum. You need to by heart the formula because we need to do numerical problems based on this formula. Derivation is important. You need to write and learn the derivation. And we also discussed 3 applications related to this law. One is recoiling of gun, second one is a man and a boat, and third one is motion of rockets. Hope the topic is clear. Make sure that you read your textbook thoroughly, write and learn the derivation part 2. Thank you.